Good morning and good day, everyone. Welcome to the inaugural TinyML Technical Forum Asia. I'm Dan Su. I am an assistant professor in Shanghai Advanced Research Institute, Chinese Academy of Sciences. It is my pleasure to welcome all of you to TinyML Asia. Now it is my pleasure to introduce Mattina of ARM. His presentation today is Tiny Yet Powerful Hardware for TinyML. Mattina is a distinguished engineer at ARM and senior director of ARM's Machine Learning Research Lab. The lab is focused on developing hardware, machine learning models, and optimization techniques to deliver energy-efficient machine learning execution on ARM devices, from server to mobile to IoT. Prior to ARM, Matt was at Tylera, Intel, and DEC, and have a lot of experience. Matt also holds a Master in Science degree in Electrical Engineering from Princeton University and a bachelor degree in Computer and System Engineering from Rensselaer Polytechnic Institute. Let's welcome Matt to share tiny yet powerful hardware for tiny machine learning. Okay, microphone's on you, Matt.
Okay, thanks, Rudan, for for that nice intro. I'll echo Jan's comments at the beginning of his talk. I'm also quite sad that we can't all meet in person in Shanghai. It's been several years now since I've been there, and I miss it, and I'm sure it's changed dramatically as it seems to change so quickly there. But yeah, so we're stuck with the next best thing, which is Zoom. Jan was calling in from Amsterdam. I'm based in Boston, so we're kind of moving across the globe tonight. It's not quite as late for me as it was for Jan, but it's getting pretty dark outside my window now. But yeah, I'm going to talk today about hardware for TinyML. My background is a computer architect, computer designer, recently moving to machine learning. And as Rudan said, I run the machine learning lab at ARM. So here's a quick outline for my talk. I'll talk a bit about what we mean by TinyML. Again, Jan did a great job motivating this. I'll give a couple of TinyML applications and benchmarks, and I'll review some more of what makes TinyML particularly challenging. And I'll talk a little bit about how neural nets and hardware can be co-designed to meet these challenges. Then I will switch over and give some examples of actual TinyML hardware platforms, and then I'll close with some thoughts on where all this might be headed. So let's get started. Yeah, so what do we actually mean when we're talking about TinyML? I sort of had a random definition in mind, but this past summer, I actually chaired a panel session at the ARM Research Summit with Pete Warden and Vijay Janappa Reddy on TinyML. And I actually asked, at the beginning of that panel, I asked Pete for what's really the definition of TinyML. And he had a very, I thought, nice response. Pete's answer to this, and the one I've adopted, is that TinyML is machine learning inference at around 1 milliwatt of power. And I actually think this is a pretty good definition. And in essence, what's going on here is we want to run increasingly complicated machine learning inference, which, in my view, is mostly about neural networks. I mean, the action in machine learning right now in the research community is on neural nets. And we want to run these models on deeply embedded devices like, say, a microcontroller. And, you know, as we'll see later on in the talk, these microcontrollers are really quite limited in several different ways. They're limited, you know, in terms of their throughput, right? We're talking about devices that can you know, run at around 250 megahertz, say. You know, they maybe can do 1 or 2 ops per cycle. So these aren't, you know, massive GPUs. So they're limited in just their raw arithmetic throughput. They're limited in their memory capacity. And also critically, they're limited in terms of power, their power budget. But even with these limitations, you know, we can do some pretty amazing things on the hardware we have today. And the hardware that's coming down the pipe is really astonishing in what it can accomplish in very tight area power and memory budgets. So with that background, let's take a little bit of a deeper look at some real applications. And for this, I borrowed from the TinyML Perf Consortium's benchmarks. So this is this benchmarking suite is an attempt to start to try to quantify hardware, right? Unless you can benchmark something, you really it's really hard to sort of argue about whose hardware is better. So you need sort of standard benchmarks, like the way SpecInt has done for CPU architecture for decades now. So on the TinyML benchmarks, there's 3 I think that are in the suite today, and those are visual wake words, speech commands like, say, keyword spotting, and anomaly detection. And these are the benchmarks that we can really focus and analyze the hardware. But I think it's also useful to think about a larger system that might include these models as part of their design. So, for example, the person not person model, well, that might be the core component in a surveillance camera type of system that maybe has intruder or no intruder running on, say, an always on processor. And when that model is maybe taking in 10 frames per second, say, of HD video, when that model detects, that always on processor detects an intruder, well, that might wake up a larger processor to do further classification of the scene. Another example that my lab, actually at ARM, collaborated on with researchers from Bose. We worked with Bose to develop neural networks that do speech enhancements on smart hearing aids. And again, if you think about these power constraints, right, you for sure don't want to burn a watt of power in your ear. So that's it gives a flavor for the types of things we want to do and these hard constraints. There's a few other examples that I've heard about in the TinyML community that kind of excite me. I've heard about earthquake detection running again on always on an always on block inside a phone, as well as car crash detection. And again, these are all from the acoustic angle. And at the end of the talk, I'll bring up my favorite candidate for a next generation of TinyML models. Okay, so with this background, let's take a look at some of the trends in neural net architecture that makes TinyML challenging. I think, one sort of hardcore fact about neural nets is that, we're seeing as we scale them up and as we train them with more and more data, their accuracy continues to improve. So these models are scaling in a pretty remarkable way. So more data, more parameters, more layers, better accuracy is how I summarize this. My favorite example of this scaling trend is actually the GPT-3 language model from OpenAI. This model has, I believe it's 175 billion parameters, and it demonstrates sort of human level performance on a whole range of really interesting language tasks. If you haven't checked it out, I recommend it. I mean, it writes poetry, for example, way better than I do. And I'm sure it does other things better than me as well. But we're seeing these larger and larger models. So GPT-3 is one extreme, but we're seeing this trend across neural network research. And this model size presents a challenge, right? We need tons of memory just to hold the static weights, right? Those 175 billion parameters. And by the way, we also need sort of SRAM or on-die memory to hold the output activations that are being produced as we move, through the network from one layer to the next. So these things are big, and there's a reason they're big. They're big because they work, and they get better when they're bigger. Another observation is that, it's not just parameter count. So parameters and op count go together. So the reason you have 175 billion parameters is you're going to use them. So these larger networks basically require more and more operations per inference. So per frame of video or per audio spectrogram that I push in, I need to do more operations to get my high accuracy result. So, I think just to make this a little bit more concrete, right? If we think about like a 1 gigahertz processor core that's executing a single precision FP-Mac operation per cycle, well, if we count the multiply and the add as 2 operations, that's just 2 GOPS per second. And if we look at some of these networks where I've plotted the sort of relative size of the network is the size of the bubble, and on the x-axis I have million of max required per inference, and on the y-axis I have the accuracy. If we take a randomly selected one like Inception v4, which is a fairly accurate image classification network, well, that requires roughly 12 billion max per inference. Okay, that's interesting. But now don't forget that we're talking about, say, 10 frames per second of video, right? So 12 gigamax times 2 for 2 ops per cycle times 10, that's 240 billion operations per second. So that's a lot if you think back to our, back the envelope calculation, a 1 gigahertz processor core, single issue getting 2 GOPS per second. So we're off by a couple orders of magnitude out of the box. And to make this more concrete, if we look at this figure here, which I took from our recent paper on micronets, this kind of gives you a feel for the space we're talking about. So like, in the cloud ML sort of segment of the market, like in a NVIDIA Volta card, you've got 16 gigabytes of memory, you've got a power envelope of 250 watts and a price tag. This probably changed a bit, but around $9,000. Now let's go to the other end of the spectrum, right? In the TinyML category, you have some, platforms from ST Micro, some with an ARM M4, M7. Well, now take a look at this. How much memory do I have? Maybe 128K, maybe as much as half a meg of on-die SRAM for holding those activations that I mentioned. And on the storage side, I've got some flash, but not a petabyte disk. I have maybe a megabyte or two, and my power budget is less than a watt, right? Like 0.1 watts or 100 milliwatts, and the price is minuscule compared to a GPU. I think the other interesting thing, as I started looking at this space several years ago and trying to figure out, where the power is going. If you look at, we're talking about here networks that are approaching, a tera-op, a trillion operations per second to compute. Just reading that amount of data from SRAM. So in other words, reading a terabyte per second from SRAM and 16 nanometer, that alone is going to burn up a watt. So you haven't done any math yet. You've just read that required bandwidth that you're going to need to feed into your data path. You've burnt a watt. So this gives some sense of, what really makes TinyML challenging. So what I want to pivot to now is looking at how we can deal with this mismatch between state-of-the-art neural networks and TinyML hardware. So we just saw that neural nets are getting larger, bigger and bigger. They require more and more computes and memory to do inference on them. So as Jan mentioned in his talk, one of the key sort of hardware-friendly advances that we've seen over the past few years has been, and this is from the research community as well, it's been demonstrating that you can take these parameters that I've been talking about, these weights of the neural network, and you can quantize those into low precision representation without impacting accuracy in many cases. There are cases where the accuracy suffers, but in many cases, you see nearly, zero accuracy loss moving from an FP32 representation to an int8. So we've seen a whole slew of reduced precision efforts. So, we've seen reduced precision floating point in the form of bfloat 16. And we now have flows in all of the major frameworks like PyTorch and TensorFlow that will quantize models down to an int8 representation. And beyond that, there's good evidence that for some types of networks, we can quantize even further. So now going below, 8-bit integer representations, there's a fair amount of literature now showing that networks can be brought down to, say, 4 bits precision without negatively impacting accuracy. And in some cases, we're seeing binary networks or ternary networks. And these, require special flows to accomplish this. But if you think about this in terms of hardware, right, this has major implications. I mean, just think about intuitively how much lower power and lower area, say a 4-bit Mac is, 4-bit integer Mac compared to an FP32 Mac. So there's massive efficiency gains by reducing the precision of both the weights and the activations as well. The second thing in our sort of arsenal of closing this gap between neural nets and the hardware is data reuse. So you know, the great thing about CNNs, now speaking from as a hardware designer, is that, you know, you're essentially sliding these relatively small filters or kernels across the 3D tensor of activations. So, you know, have my incoming tensor, you know, some X by Y by Z tensor, and now I'm sliding a small kernel across that, several small kernels across that. But what that means is that the same weight values are reused over and over again at every location in the input tensor. And really, if I were to say, you know, one thing that's the key to efficient hardware for ML and neural nets specifically, is leveraging this reuse pattern in the microarchitecture. And if you think back to my prior slide, right, I said, well, if you're going to read a terabyte per second from SRAM and 16 nanometer, you're going to consume a watt. Well, the answer to that is don't do that, right? You can leverage the reuse to directly attack that huge power cost of reading from SRAM by leveraging this fact that these weights are used over and over and over again. So moving down, you know, my list here to attack sort of the memory footprint and memory bandwidth pressure, weights can be compressed in memory and decompressed just prior to their use. So if we can compress it in flash or in DRAM, well, we can fit more now in that limited resource, and we've lowered the bandwidth, right? To pull in those weights, I now use less of that interface. And one very simple way to compress weights is by just not storing zero valued weights. As I'll talk about later, you know, we get a lot of zeros, and Jan mentioned sparsity in his presentation as well. So if I simply don't store the zero valued weights, maybe include a bit mask that indicates where the zeros and non-zeros are, you know, I've potentially cut into the memory footprint, and I've gotten better bandwidth and lower power by doing this. The next one is super interesting. So, you know, matrix multiply is really at the core of neural network math. That is, you know, 60, 70, 80% of the operations in a modern neural network. There are interesting, you know, mathematical transforms that you can do that sort of transform this order n cubed, fundamentally order n cubed matrix multiply operation into an order n squared operation. So essentially you're transforming a outer product or an inner product operation into a element-wise operation, so into an order n squared computation. And this has hardware implications. You can train your network normally, and then at inference time, you can operate in this other domain, this, you know, the Winograd domain. But this has hardware implications because you'll need to support munging, you know, the incoming weights, incoming activations. You need to transform them to this other space, and then you need to sort of do a reverse transform using these transform coefficients. But this is another way that we can attack this, you know, complexity explosion and change an order n cubed operation to an order n squared. Finally, we can leverage the fact that, you know, the widely used ReLU, rectified linear unit activation function, results in lots of zeros dynamically as I move through the network, and then, you know, downstream of that zero, I'm going to multiply by it, and one can put hardware support to not just, you know, clock gate those multiplications by zero, but actually get rid of them completely. there's sort of two important forms of sparsity, and the sort of the static sparsity in the weight space. And Jan mentioned that in his talk about, ways to prune neural networks and eliminate these redundant weights. But there's also dynamic sparsity, which arises largely due to this ReLU, which saturates at zero. Negative numbers get saturated to zero. So that's sort of a whirlwind tour of some hardware / neural network architecture techniques to close this gap between neural network compute requirements and memory requirements and the hardware. All right, so with that background, I wanted to shift gears a bit and take a closer look at some real hardware designs that are suitable for TinyML applications. And the way I segmented this out was into a couple categories, and time is limited, so I can't cover everything, but I wanted to talk about some low power general purpose cores and SoCs, some low power MicroNPUs, and finally some analog stuff. And I have some boards actually with me here that I occasionally fiddle with when I'm tired of writing PowerPoint slides. So I have a microbit, which has an ARM, I think it has an ARM M0 on it. I have an ST Micro, which has, I think it's an ARM M7 on it. So here's a picture of an actual TinyML platform. So before we dive into the actual examples, I wanted to talk about some hardware trends that I'm seeing in these three categories, in analog, in MicroNPUs, and in general purpose cores. And I think this might be the most interesting slide in the presentation, and there's no pictures. But let me walk through this. So what we're seeing in the low power general purpose cores and MCUs is we're seeing wider vector registers to support machine learning workloads. And if you spend any time around neural nets, you know that it's all about the dot product and matrix multiply operations. And the reason these wide vectors are this is such a compelling approach is because you're essentially amortizing all the front end power overhead in your processor, right? So rather than fetch 8 instructions from the iCache through the branch predictor, down to the execute stage to do 8 multiplies, if I can encode that into 2 vector registers, 2 source vector registers, and 1 instruction that says take these 128-bit registers and multiply their elements together and sum them, I've amortized the front end power cost of my processor. So that's why you're seeing this in next generation cores and MCUs. And as I said, dot product and matrix multiply, well, this is a fundamental operation in all neural networks. Neuron takes in a bunch of activations from the previous layer, multiplies it by a bunch of weights, sums those up, and pushes it through an activation function. A trend we see in the MicroNPU space is hardware support for lower and lower precision. So we're starting to see 4-bit, less than 4-bit, as well as 4-bit operations. And as I mentioned earlier, recent research is showing minimal accuracy losses with 4-bit weights and 8-bit activations. And that's important, and we've seen this in my lab as well. Like the activation precision seems to be more sensitive than the weight precision. That is, dropping below 8 bits, your accuracy on the activation side, accuracy falls off fairly quickly. We see hardware support for sparsity, zero skipping. I mentioned this on the prior slide. This arises due to the ReLU activation function, as well as weight sparsity. And you can build hardware and multiplexing circuitry to skip over these operations and get higher throughput. Hardware support for compression, weights, and activations. You know, as much as I said that it's all about the matrix multiplication and neural networks, there are other things as well that are less computationally intensive, or rather, they have a worse ratio of ops per byte read from memory. So convolution, CNNs are really good because you do lots of ops per byte read. But like the fully connected layers or depth-wise separable, those do many fewer max per byte read. And that's where we see things like hardware support for compression of weights and activations being super useful. Finally, on the analog side of things, the first commercial products are starting to appear in the space. You know, we've spent a lot of time trying to peel the onion on this and figure out what, you know, whether analog is really significantly better than digital, whether the noise issues can be dealt with in analog, and all the different options for the bit cell. And I'll talk about this a little bit more in the slides. Okay, so here's an example of a MCU Core IP. So this is Cortex-M55. This is ARM's most AI-capable M-class processor. We target a bunch of TinyML use cases with this core, like health trackers, smart speakers, and things like video doorbells. But I like this to motivate, you know, what I just talked about in terms of the vector extension. So the big deal with this piece of IP is the new Helium vector extension for M-class. And this is really the key to achieving high performance in a low power budget. So this vector extension defines 8 vector registers. They're 128 bits wide. So you can pack, 16 int8 values into a single vector register. And these, of course, come with over 130 new vector operations that actually use these wide vectors. There's a range of precision data types that are supported. And as I said, like if we have, you know, a quantized network with say 8-bit integer weights, we can pack 16 weight values into one vector register, 16 activations into another. And then we can add these vector registers together using a new vector MAC operation. And what I'm showing here on the right is the speed up for the Cortex-M55 on a keyword spotting neural net model, CNN based. So we're getting like, we're seeing like, you know, 8x higher throughput versus previous generation Cortex-M4. And this is using the library that Jan mentioned previously called SimSysNN, which is essentially a collection of kernels that are highly optimized for M-class processors. And on the lower left, I'm just showing, you know, schematic of these vector ops. So we're taking, we're taking, you know, this element from the green register, this element from the blue register, multiplying them together. Same with these next elements, multiplying them together, and finally accumulating this into a, in this case, a 32-bit output. Okay, so prior slide, we looked at a single core IP block. I also wanted to look at like a full-on MCU suitable for TinyML workloads. And this This MCU was presented at TinyML Summit 2019. This is from Greenwaves. It's called the GAP8 applications processor. This guy has 8 32-bit RISC-V cores, has a max frequency of 250 megahertz in TSMC55 low power process. And this design is super focused on low power. And I thought this was really interesting as I was, reading up on this for this talk. This design, as I show here on the right, the block diagram, there's no D-side caches. So there's a I cache, a shared instruction cache that all 8 cores read from, but there's no data side cache. And if you think about the implications of that from a power perspective, right? If typical cache, you're reading out a couple of ways per read. You're reading out the tags. You do a tag comparison to figure out if your load hits in any of those ways. All that power goes away if you're not building caches on the data side. So what do they do instead? This design relies on DMA engines for explicit data movement. So essentially, if you can see my cursor, but there's a cluster DMA engine here. So it's software-driven DMA engine that pulls data out of the L2 memory and sticks it into the shared L1. The other things like the M55 that we just talked about, these cores, these 8 RISC-V cores here also have a RISC-V vector extension. They support 8, 16, 32-bit fixed point. And I don't think there's floating point support for this design. The other really interesting thing about this is this design integrates a hardware convolution engine shown over here, sitting alongside the 8 cores. This is a dedicated hardware block. It has 112 multipliers, and it delivers a 3x performance gain over pure software running on the 8 RISC-V cores. And the hardware convolution engine is capable of executing a 5x5 filter, which is common in many neural nets, with 16-bit weights, 16-bit activations in a single cycle. So 5x5 conv, single cycle result. And sort of the bottom line number here is they can achieve around 236 billion operations per second per watt. And on the specific keyword spotting CNN benchmark, using this hardware convolution engine, they dissipate just over 1 milliwatt of power. All right, so we talked about IP, core IP. We talked about a full SoC or full MCU. Let's talk a little bit about NPUs now. And this is sort of a new class of MicroNPU. So these aren't giant NPUs that go into like a mobile phone, but rather much smaller, sort of less than a millimeter squared of area. So one example of this is Samsung's Edge NPU design. They presented this at TinyML Summit, I believe, earlier this year. This is a scaled down version of Samsung's mobile NPU, and it targets Samsung wearables. Their big NPU, I believe, has over 1,000 max. This one is significantly cut down, has 128 max with 1 NPU core. And I like this because it's an example of sort of co-designed hardware software design where they specifically looked at executing binary neural networks and networks that use grouped convolution. And they scaled these parameters way down to like binary or ternary weights. And they similarly scaled their multipliers way down inside the design as well as their accumulators. They also include a hardware weight decompressor And at the end of the day, they're claiming around 24 trillion ops per second per watt in this design. Now, a top here and a top here, you know, a mobile NPU top is not the same as an edge NPU top, since the tops here are much lower precision. But you know, we're seeing examples of very large numbers of operations per watt. Okay, so from ARM, ARM's NPU family is called Ethos, the Ethos-U family. These NPUs are designed to work right alongside the Cortex-M class and A class CPUs. The U65 has 512 Macs in the design. This is the Mac engine shown here. And it has a peak throughput of over 1 trillion ops per second. And these are 8-bit weights. So these are 8-bit tops. And the activations can be either 8 or 16 bits. This design also includes a weight decoder. So we support, in this design, we support compression of weights. They're decompressed before being fed into the Mac engine. And again, this enables, you know, better usage of memory. You can fit a bigger model in a limited flash or SRAM, as well as more effective memory bandwidth. So bottom line, the U65, which is the latest IP block in the Ethos class, delivers over 1 trillion ops per second in well under a millimeter squared in 16 nanometers. So in 0.6 millimeters squared, we're getting 1 trillion operations per second. And there's a quick summary of the performance on the wave to letter and MobileNet, well-known MobileNet benchmark. This pairing the Ethos U55 with a Cortex-M55 gives you 150x speed up over just a Cortex-M4 alone. So we're starting to close this gap between, giant neural networks and what can actually be delivered in a very low area budget. All right, final section on hardware. In-memory compute analog. This is a space I'm very interested in. There's a lot of amazing claims. I have this graph from ISSCC showing, phenomenal tops per watt and per millimeter squared. I think it's useful to look at, what we can do with a purely digital solution. Bill Daly had a nice paper a couple years ago where they showed that, roughly you can get 200 tops per watt from a pure digital solution with 3-bit weights, log encoded weights in 60 nanometers. So for me, that's the first bar. Like an analog solution needs to be much better than this out of the gate. This is a super hot research area. I've seen, papers using resistive RAM, phase change memory, lots of different things for the bit cell itself. There's some really prickly analog noise issues, but maybe we can architect the neural net to be robust to this noise. And my group also published some work on this space around, building the noise into the training process, so as to cope with a noisy hardware and inference time. There's lots of issues with the ADC and the DAC, power and precision. How programmable are the analog solutions? People often forget too, like you still need to, unless you're going to flatten your entire network into the analog design, you're going to need to bring the parameters, time multiplex, essentially the memory array. That has a power cost. You need to pull those parameters from somewhere. That's not free. And never forget Amdahl's law. Neural nets are not just matrix multiply. So I wanted to just quickly show the basic idea behind the in-memory compute approach. We want to store, weights in this memory array. Let me just build this out. In this memory array that I have highlighted here in red, we're going to send activations in, like from the previous layer, essentially as on the word lines through a DAC, digital analog converter. Each cell is going to do some kind of analog multiplication for the activation against the stored weight, and the resultant currents will sum together on this bit line, and that's essentially a neuron's output. So almost all of the analog compute in memory approaches I've seen are doing this in some form or another. So if we look at a little bit more detail on how you actually map a modern CNN to an analog crossbar, we have these filters in a CNN that I mentioned earlier. Essentially, we're going to place those filters, like here's the yellow filter. These become columns in the array. So I basically linearized these filters into vectors, stored them in the array columns. I'm going to slide in image patches along the Y dimension. And then at the bottom of each column, I'll have an A to D converter that senses this current and gives me a digital sum out. So basically, the analog compute in memory designs follow this form with some variations on this theme. And the commercial product from Mythic is one of the more prominent analog approaches. This is a flash-based compute in memory accelerator. This thing can hold 113 million weights, 8-bit precision. There's a ton of A to Ds, D to As on the die, but they've also put a programmable block as well to handle all the non-MAC component of neural nets, so like element-wise and ReLU. And so according to Mythic's literature, this design is delivering 35 TOPS. It comes in at around 4 trillion ops per second per watt in this PCIe M2 form factor. And they demoed this last month at the AI Hardware Summit, and they actually showed a version of ResNet 50 running on their design. So I think it's very exciting to see actual working silicon in this space, to give some empirical evidence that this can be done. All right, so let me wrap this. I've been building processors for over 20 years now. I find it useful to actually step back and reflect on the fact that we're seeing hardware today, in 2020, that delivers trillions of multiply operations per second in less than a millimeter squared of silicon. So 1 trillion multiplies in a second in less than a millimeter squared of silicon, burning less than a watt of power. And I think that's incredible. I expect it over the next 12 to 18 months, we're going to see brand new applications for TinyML that really start to take advantage of this hardware to deliver amazing things. An example I saw 2 weeks ago that really struck me is that some researchers at MIT have developed a neural network model that actually diagnoses COVID based on the sound of people's cough. And it's actually 98% accurate, even with asymptomatic people. So these are people who don't know they have COVID, but by training this model that listens to the sound of their cough, the model is able to predict that with 98% accuracy. And I dug into this a little bit, and it's very interesting. I put the reference here, but the design actually uses 3 ResNet 50s. ResNet 50 is a well-known image classification model. 3 ResNet 50s running in parallel. So that's not tiny, that's a lot. But imagine if we could get this to run, always on your phone or on your watch, burning very little power. I think that would be a phenomenal result for the world. And I expect we're going to see that hopefully soon. The other interesting trend that we're working on inside of ARM in my lab is this co-design of neural networks and hardware, and especially neural architecture search. So I put a link to our recent paper here, but we're using neural architecture search to find models that specifically fit very constrained platforms. So this graph is showing here for visual wake words, we're using differentiable NAS to find models that fit in various tiny hardware platforms. In the middle graph, I'm showing the SRAM constraint. So we show the SRAM constraint of an ST micro board there of around 100K. We tell our tool we want a model that fits in less than 100K, that's as accurate as possible, and the tool goes off and finds that. I think this is going to be super useful, and we're finding state-of-the-art models in this fashion. So with that, thanks for listening, and I'm happy to take any questions.
Thank you, Matt. I know it is really late in Boston time. It's approaching midnight, right? Thank you for your sharing.
Yeah,
and
pleasure.
Is there any question for Matt? You can post in the, yeah, we got question. So a quick question, besides Mythic, is there any other example works under 1 microwatt analog or computing memory ICs? Is there any other example?
I'll give you 2 references that I think approach that. IMEC in Europe, which is a foundry, they've published some stuff at ISSCC on their compute and memory approach. So they, to publish at ISSCC, you need working silicon. So they've built some prototype chips that approach, I believe it was 1,000 TOPS, over 1,000 TOPS, so a petaop per second, and I don't quite remember the power of that device. So there are definitely people getting close to that space. I think the thing I would say is that there's more than just the array, right? You might be able to demo an array that can do, a huge number of ops in a very low power, but you need to account for everything else, all the D to A's, A to D's, all the time multiplexing cost of moving weight parameters in and out of the array. And I haven't seen anything that approaches that microwatt for a full solution yet.
Okay, thank you for the reference. I think this is very valuable. And the second question is from Jack Zhang. What is the difference between MPU and embedded FPGA, both as an accelerator alongside MCU?
That's a really interesting question. Let me take the FPGA part of that. I see 2 approaches with FPGAs. One approach is called an overlay architecture, where essentially in the FPGA, you build an NPU, but except now you're building it out of LUTs and out of FPGA stuff. So by definition, that's not going to be as good as an NPU in terms of area, cost, power, because an NPU is essentially an ASIC. The other approach, so the approach number one is like build an NPU in your FPGA. The other approach is actually implement a custom data path in your FPGA that exactly solves the neural net problem that you have. So if all you ever want to do is keyword spotting, then you can sort of burn your keyword spotting neural network directly into FPGA. And if you do that, you can get great efficiency because, like, you know your weight parameters, right? You might have a weight that's 7 at one place. Well, you can just implement the multiply by 7 in the FPGA as is. And of course, you can get great efficiency that way, but it's much less programmable. So there's a trade-off between programmability that you get with more modern NPUs and uber performance if in an FPGA if you just implement exactly the neural net you care about.
Okay, thank you. And I got a very long question, and I already asked the first part of it. What would be a good way for the students, undergraduate or master students who are interested in the field of tiny machine learning? Do you have any suggestions for them?
Yeah, it's a great question. The reason I think it's a great question is because I asked the same question at a panel that I ran over the summer. I asked the participants the same question. I think you actually alluded to it in your question. I think a couple things here. There's just a ton of stuff online, like Google's Colab comes to mind. Some of the Stanford courses come to mind. There's just a ton of stuff that's available today for learning about this. But in my view, there's no substitute for actually doing it. And as you mentioned in your question there, you can get these boards, for super cheap. Some of these boards, like from ST or the Microbit, and I'll say that the tool chain is really getting there now. Especially big shout out to Pete with TensorFlow Lite Micro. It's matured significantly to the point where now, I mean, even in my lab, we struggled getting TinyML stuff running on this hardware a few months ago. It's much, much better now. TensorFlow Lite Micro is much better. So I would say get some of these boards and actually use TensorFlow Lite Micro and get some stuff running on the real hardware. It's the best way to learn.
Thank you, Matt. Thank you for the suggestion. Okay, since time is limit, we will go next step. Thank you, Matt. I'm really looking forward to meet you next year in Shanghai, TinyML Asia.
I look forward to that too.
And have a good night.
Thank you.
Yeah.
Thanks, everyone.
Okay, thanks. So we would like to thank our sponsors who made this event possible. Our premier sponsor, ARM, the Software and Hardware Foundation for TinyML. Cortex, with dynamic neural accelerator architecture and co-exploration engine brings cloud level performance to the edge. SynSense builds ultra low power sensing and inference hardware for embedded mobile and edge devices. Thank you for all our sponsors. Thank you for making this event possible. And thanks also go to our conference partner, Shanghai AI, a media partner, 智东西 AI in Manufacturing, EET, 机器之心, 新视野, and 机械工业出版社. Thank you for our partners. You will find them all listed on the TinyML website. at tinyml.org. So thank you for joining us today. And thank you for Jan, and thank you for Matt, and for Evgeny for their wonderful presentations. We look forward to seeing you tomorrow.